In the heart of the absolute cold of space, somewhere 160,000 light-years away from us, molecules in the ice are combining. Molecules that could be the initial building blocks of life, not on Earth, but in another world, in the Large Magellanic Cloud. And now, for the first time, the James Webb telescope has been able to see these complex organic molecules like methanol, ethanol, and even acetic acid from that incredible distance. But how is it possible for a telescope to detect such delicate things from that insane distance? What makes this discovery so exciting for scientists? And most importantly, does this mean we are truly not alone? Get ready, because we're about to journey into the depths of the cosmos, where science and mystery are intertwined, and the new discovery by James Webb is redefining the boundary between chemistry and life. Join me on the Astreyon channel. The James Webb telescope has looked at a neighboring galaxy and found molecules like methanol, ethanol, acetic acid, acetaldehyde, and methylformate in the ice around a protostar called ST6. These molecules, known as complex organic molecules, or COMs, are potential raw materials for biochemistry, meaning things that could form the initial foundations for living things. The distance to the Large Magellanic Cloud is about 160,000 light-years from us, and this is the first time such molecules in ice outside the Milky Way galaxy have been definitively identified. Now that we've introduced this discovery, a question arises. How did JWST identify these molecules? JWST uses the mid-infrared instrument, or MIRI, and the medium-resolution spectroscopy, or MRS mode, to analyze the infrared spectrum of light. That means, instead of just taking pictures, it breaks down the light and looks at which parts of the light are absorbed by molecules. These absorptions act like fingerprints for each molecule and show what's there. For ST6, researchers saw signals from ice on cosmic dust grains that include these molecules. And this method is very precise and sensitive. But it requires clean, high-quality data. For example, for acetic acid, this is the first strong detection in ice around protostars outside our galaxy. This way, JWST sees the molecules without direct imaging. Now we can get into what's happening in that dust cloud and how these molecules are being made. The protostar ST6 is trapped in a cloud full of dust and ice, and these dust grains, smaller than a grain of sand, act like tiny laboratories. In the extreme cold of space, simple molecules like carbon monoxide and methane freeze and stick to these grains. Then, ultraviolet or UV rays from surrounding stars come and provide energy so these molecules combine and create more complex things like methanol or ethanol. This process is called cosmic chemistry, or interstellar ice chemistry, and it shows that the universe can create potential raw materials for biochemistry without needing a planet. An interesting point is that even in the Large Magellanic Cloud, where there's less carbon and oxygen and UV rays are much stronger, this happens. This tells us that the chemistry of these molecules is very robust and can survive in harsh conditions. It's like the universe has built an automatic factory for creating potential building blocks of life. Recall the Miller-Urey experiment from the 1950s. Scientists put simple gases like methane and ammonia in a container, simulating Earth's early atmosphere, then added energy with electrical sparks like lightning, and saw that organic molecules like amino acids were formed. The universe is doing something similar, but on a much larger scale and with important differences. The main difference is that Miller-Urey works in Earth's warm, humid atmosphere with electrical sparks, while cosmic ice chemistry happens on dust surfaces with UV radiation or cosmic particles. This is a conceptual similarity. Both show how energy turns simple molecules into complex ones, but their methods aren't exactly the same. This JWST discovery strengthens the idea that biochemistry can have various ways to start. Perhaps even some molecules on Earth came from space. Every time the James Webb Telescope looks into the depths of space, it's actually watching the past of the universe, when stars were just being born and the raw materials of life were forming for the first time. The fact that today we could see molecules like methanol, ethanol, and acetic acid in the Large Magellanic Cloud means the universe is naturally building compounds that could one day become the foundations of life. This discovery makes the possibility of living beings elsewhere not just possible, but a much more realistic probability. When these molecules form around young stars, the story doesn't end. It's just the beginning. Over time, comets and meteorites carry them into space and deliver them to newly born planets. This is where exoplanets come in, worlds outside our solar system. The James Webb Telescope has already found signs of a possible atmosphere on TRAPPIST-1e, a planet roughly the size of Earth, in a zone where the temperature allows liquid water to exist. Or, for example, GJ251c, a planet slightly larger than Earth that has stable conditions for forming organic molecules. These planets could be the natural destinations for these icy molecules. When the ices warm up and gases are released, organic compounds can spark the first flames of life. In JWST data, signals must be separated from noise, and each molecule has its own specific spectral signature. So yes, there's always a chance of error. But the power and precision of the James Webb tools have made these results much more reliable than before. And most importantly, this is the first time such molecules have been identified in ice outside our galaxy, meaning the chemistry of life isn't unique to the Milky Way, but flows throughout the universe. And when we put all these signs together, from organic molecules to planetary simulations and the discovery of exoplanet atmospheres, a bigger picture appears before our eyes. Life must exist somewhere out there. But if everything is so prepared for it, if the raw materials of life exist in other galaxies too, then why haven't we seen anyone yet? Why don't we hear any sound from the other side of the stars? This is where we enter one of the deepest mysteries of science. Enrico Fermi, the famous Italian physicist, said in 1950, "Well, if life should be everywhere, then where is everybody?" And from then until now, scientists have been searching for an answer to this question. The universe is 13.8 billion years old, and just in the Milky Way galaxy, there are over 400 billion stars, many of them with planets in the habitable zone, meaning where liquid water can exist. The probability is very high that life has formed elsewhere, but why haven't we received any signals from them? One pessimistic answer says, maybe many forms of life remain at a simple level, like microbes, and advanced civilizations are rare. But another more logical and appealing view says, advanced civilizations probably exist. We just don't have the tools or understanding yet to see them. Maybe they use technologies beyond our comprehension, signals that we simply don't understand or even notice. They might operate in different space-time dimensions, or have consciously decided to hide themselves. This idea is called the zoo hypothesis, meaning we're like animals in a zoo and they're just watching us without direct interference. On the other hand, the Great Filter theory says maybe civilizations usually don't pass a dangerous point, somewhere between high technology and self-destruction. But maybe we've passed that filter. Or maybe other civilizations have passed it before and now live in chosen silence. If we take a more optimistic view, this silence might not be a sign of the absence of civilizations, but a sign of the vast technological distance between us and them. On a cosmic scale, there might be civilizations that harness the energy of entire stars, or even galaxies, something called Type 2 or 3 civilizations on the Kardashev scale. And maybe the signals are already around us, but we don't know how to translate their language yet. These JWST discoveries about biochemistry in other galaxies are actually a sign that the universe itself is building the beds for life. So maybe the right question isn't, are we alone? But rather, when will we finally learn to see the others?